Hello people, welcome back, and today we're going to be looking at the AQA Spec part 4.3, which is Quantitative Chemistry. In the Kerbudo books, you're looking at chapter 4, so we're going to be looking at relative molecular mass, calculating moles, and all of that, so let's jump into it.
It was a nightmare.
Activate.
Right, so 4.3 Quantitative Chemistry. This is what we have, AQA Quantitative Chemistry, and then we have Kerbudo chapter 4, okay? So to start, we're going to be looking at the conservation of mass and the balanced chemical equation, okay? And these essentially, you're gonna look at the law of conservation of mass that states that whatever you put in is the same amount that you're gonna get out in a chemical reaction at least, okay? So if you have, for instance, 1 gram of magnesium and reacts with God knows 2 grams of oxygen, what you're going to end up with is 3 grams of magnesium oxide as an example, because whatever you put into the reaction is what you're going to get out of the reaction, okay? So if you have, I don't know, maybe 35 atoms going in as reactants, you're going to have 35 atoms coming out as products as well, okay? So that's essentially what conservation of mass is, okay? When it talks about the relative formula mass, as we all know, an atom has a mass number, okay? The mass number accounts for the protons and the neutrons that you find in the nucleus of the atom. Now, for instance, if you have an atom for a specific element, you look at the mass number, and that's going to tell you how much it weighs in atomic mass units, okay? But the relative formula mass is when we are counting the mass of all the elements, all the atoms that form a compound. So for instance, if you have a relative atomic mass of oxygen, which is 16, and oxygen gas molecule is O2, so you have 2 oxygen molecules in there, so you have 16 plus 16, that gives you 32. So when you add the relative atomic mass of one oxygen with the relative atomic mass of the other oxygen, both together gives you 32. So when we count it as a compound, right, the relative formula mass of an oxygen molecule, which is O2, is going to be 32 atomic mass units, okay? And that's the difference there. Relative atomic mass is when you are finding out how much mass there is in an atom, in a specific atom of an element, but we call it relative formula mass once you're looking for the actual mass in a compound, okay? Something like water, that you have oxygen, which is 16, and you have 2 hydrogens with 1 each, so it makes a total of 18. So the relative atomic mass of oxygen is 16, the relative atomic mass of each hydrogen is 1. So when you join them together as a water molecule, the relative formula mass of the whole molecule is going to be 18. 16 from the oxygen and 2, which is 1 from each hydrogen atom that we have there, okay? Now over here we got mass change when reactants or mass change when a reactant or product is a gas, okay? Now what this basically tells you is that sometimes when you have a chemical reaction, you're gonna have some of the product given off as a gas, okay? So there is no way that you could actually put it on the scales and weight and make sure that it's the same amount. For instance, if you are going to be reacting or making a thermal decomposition of calcium carbonate, some of that is going to be calcium oxide, and then you're going to end up with carbon dioxide. The carbon dioxide is going to go off away, right? You won't be able to weight that, so you won't be able to very easily tell that the reaction has happened, and then the same amount that you put in is what comes out. And it seems for a moment that the law of conservation of mass is broken, but it's not that. Unless you do it within a container in which you can actually collect the gas and measure the amount of gas being produced, then you will realize that whatever you put into a chemical reaction is what comes out of the chemical reaction, okay? Regardless whether that product is going to be a solid, a liquid, or a gas, okay? That is basically some of the things that you might get into these kind of questions in the exam. Is they might ask you to plan an experiment. They might give you some results. They might give you a statement like, I don't know, maybe David says that the law of conservation of mass was not present in this experiment because he added 2 grams of one substance, 2 grams of another substance, and as a product he only ended up with 1.5 grams. All right, so that in that occasion, you were there to explain that some of the mass got lost in the product because it was given off as a gas, but the low conservation of mass did play its part in that specific in that specific part. Okay, so that's something that you want to look at. Students should be able to explain any observed changes in mass in non-closed systems during a chemical reaction, given the balance symbol equation in the reaction, and explain these changes in terms of particle model. Okay. So it's important that you familiarize yourself with the particle model. You might have to draw a particle model explaining what happened. And this here, where it says a non-enclosed system, this is what we're talking about, that you won't be doing the practical or the experiment in a location where you can actually trap the gas that is being produced, but you need to know that the gas was produced, is not there anymore, but you just gotta put it in words, okay? Like here, the thermal decomposition of a metal carbonate, just what I said, the carbon dioxide is produced and escapes. Although you can't see it and you can't weigh it, it doesn't mean it wasn't produced, okay? It doesn't mean that the law of conservation of mass didn't actually took place. Now, chemical measurements, whenever a measurement is made, there is always some uncertainty about the result obtained. Students should be able to represent the distribution of results and make estimations of uncertainty, and use a range of set measurements about the mean and the measure of the uncertainty, okay? Now in this here, they might give you a couple of examples. They might ask you to calculate a mean or an average, right? And you gotta make sure that in the table of results you don't include anomalous results, okay? If they give you 4.1, 4.2, 4.0, 4.6, 4.21, right? That 4.6 is an anomaly because it's very different to the rest of the other results. So you would not include that when you add all of them values together and then you divide by the same amount of values that you added together, okay? So you add 4.1, 4.2, 4.3, 3.9, but you wouldn't add a 4.6. All right, because it's very different to everything else that you have. So that's why you wanna try and find out the patterns or make estimations about what the results actually are telling you. Okay, now in 4.3 it says use the amount of substance in relation to masses of a pure substance. So chemical amounts measured in moles. The symbol for units mole is MOL. The mass of 1 mole of a substance in grams numerically equal to relative formula mass. Okay, so when we're talking about the mole itself, we know the Avogadro's number, which is 6.02 times 10 to the power of 23. That basically tells us that in 12 grams of carbon, you get a bag of carbon, you weigh in it in scales, you weigh exactly 12 grams. In those 12 grams, you're going to have that many atoms. You're going to have 6.02 times 10 to the power of 23. So that is 6.602, and then you're gonna have 23 zeros following behind, okay? And that is the mole. The mole is basically a name given to a number, just like you have a fiver, which is a 5, which is a fiver, 20 a score, a dozen is 12. You have 6.02 times 10 to the power 23, and that number is given the name the mole, okay? Now you should be able to calculate the relative formula mass in all of those substances. So for instance, if you have mass of 1 mole of a substance in grams in numerical equal to the relative formula mass, okay? So if you have 1 mole of carbon, for instance, like we said, all right, carbon is 12, okay? So in 12 grams of carbon, you're gonna have a mole, and that's going to be the number that you're looking at, okay? When we look at here, students should understand what the measurement of amounts in moles can apply to atoms, molecules, ions, electrons formula, and the equation. For example, that 1 mole of carbon, the number of atoms and same number of molecules in 1 mole of carbon dioxide. So you're gonna have to be very clever about how you link one and the other, okay? You're gonna make sure you are familiarize yourself with balancing equations. I'm gonna put a link in the description somewhere here, and then you'll be able to click on it, and it will take you to a video where I done some balancing equations, and it just helps you to get around the difficulties of balancing equation. Okay, so it said that the student should be able to use the relative formula mass of a substance to calculate the number of moles in a given mass of that substance, and vice versa. Okay, that's what you want to look at. Okay, when we're looking at amount of substances, this is only for higher. All right, it tells you here that the student should be able to calculate the masses of substances shown in a balance equation, and also to calculate the masses of reactants and products from the balance symbol equation and the mass given as a reactant or product. Okay, this is very straightforward. If you understand what the relative formula mass is and how to calculate it, this should be very easy, very straightforward. Okay, so you just might need to practice a little bit on that. Okay, so for instance, over here you got magnesium. Magnesium, I believe, is relative atomic mass is 24. All right, and then H is 1, chlorine is 35.5. Okay, so what you would do here is that you have 24 from magnesium plus 35.5 of chlorine plus 2 of hydrogen, of 1 of hydrogen, but because you got 2, that means that this whole molecule get multiplied twice. So 35.5 plus 35.5 plus 1 plus 1 plus 24. All of that together is going to be the mass in the reactants. And obviously, as whatever you put in is what you're going to get out in the reactant. So whatever amount of atoms you have in the reactants is the same amount of atoms you're going to end up in a product. Is going to be same in both sides. Okay, that's what you want to have a look at. They might ask you to calculate the percentage of each one of those. So you're going to say, for instance, when you add all of these masses and then you think 24 for magnesium, what percentage is 24 from the whole of this, right? And that will be the percentage of magnesium that is going to be present in the reactants, and the same way in the other side. Okay, that's the way that you want to calculate those things. Now down here we got using the mole to balance equation. Again, this is only for higher, and it says that a student should be able to balance an equation given the masses of the reactants and products, and a student should be able to change the subject of the mathematical equation. Okay, now again, if you familiarize yourself with how relative formula mass is calculated, you should have no problems in identifying all of these bits. Okay, so it's very important that you practice on that. I'll be making some videos on how to do this specifically. Right now, just wanna go over the things that you need to know for the test. Okay, because a lot of the time you'll be studying things and not very relevant. You still need to know them, but you can't focus too much on them because in the exam you won't be asked too much about those specific bits of the topics. Okay, now when you hear limiting reactants, this is for higher only as well. In this one, it says that students should be able to explain the effects of limiting quantities of reactants on the amount of product it is possible to obtain in terms of amounts of moles or masses in grams. Essentially, this is telling us that if you are, for instance, reacting two chemicals and you run out of one of the chemicals, or there is not enough of one of those chemicals, that's going to be the limiting factor. Okay, because you don't have any more of that, you can't produce anything else, you can't be producing any more of the products. Okay, that essentially is that limiting reactants. Okay, so the limited amount of the reactants is what is going to stop more product from being produced. And again, this is only for the higher tier. Now, concentrations of solutions, you should be able to calculate the mass of a solute given in a given volume and a solution of known concentration in terms of mass per given volume of a solution. Okay, you need to familiarize yourself here with conversion of units. Okay, it's very important that you familiarize yourself with milliliters, centimeter cubes, decimeter cubes, how to turn grams into kilograms and so on. It's very important. Okay, because this is where you're gonna lose a lot of the marks, just because you are getting confused in the changing of these units. Okay, for higher only, you're gonna have to explain the mass of a solute and the volume of a solution in a related to the concentration of the solution. Okay, so this is the mass links to using ratios, fraction, and percentages, and changing the subjects in the equation. Okay, you're gonna have to learn how to do that as well. When when we're looking at here, we looking at percentage yield. Now this here is one of the formulas that you want to remember. A lot of the time it's going to be given to you. It's just a matter of you reading the questions properly and make sure that you put the values exactly where they're meant to be. Okay, the mass of the product actually made, it will be given to you. The maximum theoretical mass, it will be given to you. Okay, and you just gotta put the numbers, and that's it. You're gonna get your percentages. Okay. Calculate the percentage yield of a product from an actual yield of the reaction. Now, the actual, what's called the theoretical yield, you calculate that yourself, right? Using the relative formula mass, and then they will give you the results of the actual experiment, and this is what you actually made. You divide those two times 100, you got your yield. Okay. For higher only, you're gonna have to calculate the theoretical mass of the product from the given mass of the reactant and the balance equations for the reaction. Okay, this probably gonna take you a step further into the first part over here. But again, if you are doing higher, you should be a little bit more familiar with the next steps. Okay, it's just a matter of making sure that you read the questions properly and you put the correct figures in the correct size of the equation. Okay. Atom economy. Atom economy key is atom utilization, which measures the amount of starting material that end up as a useful product in the important for sustainable development and economic reasons due to reaction with high atom economy. Okay, essentially this is like when you react to chemicals because you want a specific product. Sometimes that chemical reaction will give you a byproduct. So there may be ways in which you can conduct the same, a different chemical reaction and produce the same products or similar amount of products. Okay. So for instance, there is one example of production of alcohol from fermentation against the production of alcohol from cracking. So both of those will give you alcohol. It's just that one of them will give you a higher yield where everything gets actually used up and turned into that desired product, and the other one's gonna have some byproducts that you don't really want, and that's what you want to look at. Okay, you should be able to calculate that. For higher only, you have to explain what a particular reaction pathway is chosen to produce a specific product given the appropriate data, and this is what I'm telling you about. You might be given the example of the alcohol yield, you might be given an example of ammonia as well being produced. You make sure you check a couple videos on YouTube about how those processes work. Okay. Then we're using concentration of solutions in moles per decimeter cube. This is for higher only as well. You need to familiarize yourself with how to dilute a substance. Okay, you gotta make sure that you understand what concentration is and how much a dilution is going to affect the concentration in a specific substance that they have asked you to dilute. Okay, you're gonna make sure you understand volume measurements, decimeter cubes, and so on. Yeah, and that's about it on that. We still continue with here we got use the amount of substance in relations to volume of gases, and this is for chemistry only, higher tier as well. And it says the equal amounts of moles of gases occupy the same volume under the same conditions of temperature and pressure. The volume of 1 mole of a gas at room temperature and the pressure of 20 degrees and 1 atmosphere is 24 decimeter cubes. The volume of a gaseous reactant and products that can be calculated from the balance equation for the reaction. So the student should be able to calculate the volume of a gas at room temperature and the pressure from its mass and relative formula mass. Again, this here is something you need to relate yourself to. You need to make sure you know how to read the periodic table to extract that information. Okay, and then you have to calculate the volume of gaseous reactants and products from the balance equation and give the number of volume gases, reactant or product. You change the subject mathematical equation. Okay, there's a lot of maths involved in here, so you gotta make sure you do a couple of exercises, you get some practice on this, and I believe you should be okay. At some point I'll be making videos on how to get more in the specifics and give you examples how to answer exam questions in these specific topics, but until then, that's all we got for now. Okay, I hope this video was useful and I hope you enjoyed it, and if you did, like and subscribe to help us promote the content. And then if you have any questions, drop us a comment and I'll get back to you as soon as I can. And as always, knowledge is power.